Hello everyone, myself Varshita BK. I'm studying in Bangalore Institute of Technology. I'm explaining the concept about decoder problem concept. In this video, I am gonna explain about what is a decoder, functionality of decoder, application of decoder, importance of decoder, implementation of 2 is to 4, 3 is to 8, 4 is to 16 decoder, and implementation of half adder, full adder, full subtractor, half subtractor with the help of decoder. Definition of decoder. A decoder is a combinational logic circuit in digital electronics that takes a binary input signal and activates specific output lines based on the input pattern. Here, combinational logic circuit is the combination of AND gate, NOT gate, NOR gate, AND gate, and many other logic gates. Decoder is a combinational circuit where we pass n input lines and produces 2 to the power of n output lines. One of these outputs will be active, high, based on the combination of inputs present when the decoder is enabled. For example, if you pass 2 input lines to the decoder, then maximum possible output that decoder can form is 4 output lines. One of these output will be active high based on the combination of input present. That means that decoder detects a particular code. The outputs of the decoder are nothing but the min terms of n input variable lines whenever it is enabled. Functionality of decoders. The primary function of the decoder is to take the binary coded information and activate specific output line based on the input pattern. There are many functions of decoders such as data routing, control signal generation, address decoding, function selection, data conversion. Here, data routing enables the selection and routing of data within the digital circuit. Control signal generation plays a crucial role in generating control signal for coordinating various operations within the digital system, such as input pattern, activating the output signal with the help of uh, enable input signal, address decoding in memory system and many other devices. Decoder are used for address decoding. Functional selection. Decoders are often employed to select specific function or operation based on the input condition by decoding input signals. Decoder determine which function to activate or enable, allowing for flexible operation and configuration of digital system. Data conversion, it is very helpful to convert binary coded decimal input into corresponding decimal or alphanumeric representation. Here is the representation of the decoder. We are passing n input lines. Hence, there are 2 to the power of n output lines. This is the decoder where there are combinational of logic circuits such as AND gate, NOT gate, OR gate. If we pass 2 input lines, then there would be 4 output generated, in which one output would be active whenever the enabled input is at a high state, and other output signal would be 0. Types of decoder. Binary decoder are one of the most types of decoder. They have multiple input lines and produce multiple output lines, each corresponding to unique combination of input states. BCD decoder. Here, BCD decoder are specialized decoder designed to decode binary coded decimal inputs. BCD is a binary representation of decimal numbers where each decimal digit is represented by its 4-bit binary equivalent. Third type of decoder is 7-segment display decoder. Here, 7-segment display decoder are specialized decoder used for driving 7-segment displays. Here, we pass 4 input signal as represented in this figure A, B, C, D, and we get 7 outputs. This is mainly used in calculator, digiclocks, and other display devices. This is the truth table representation of 7-segment display decoders. I have represented one example of binary decoder where we pass 2 input lines and we get 4 output signal Q0, Q1, Q2, Q3, where Q0 to Q3 are the mean terms of 2 inputs, where 2 inputs are combined in this decoder in a unique way. BCD decoders representation, this is the representation. Implementation of decoders, how the decoder is implemented, what are the things present in the decoder. It contains input lines, decoder logic, output lines, truth table. The input lines is produced to the decoder where we pass n input lines and then represent the number of input lines. Decoder logic. The decoder logic typically consists of AND gates and inverters. As I said before, that decoder is a combination of logic circuit. Hence, it consists of AND gate and inverters mainly, arranged in specific configuration based on the desired decoding function. Here, output lines. The decoder has multiple output lines, usually labeled as M, where M is equal to 2 to the power of N, where N is the number of input lines. If we then where M represents the number of possible output states. Each output lines corresponds to a specific combination of input state and it is activated when the input pattern matches the corresponding decoding condition. There is certain input pattern that has to be matched, then only the output signal would be enabled. That is, whenever the enabled inputs are active, then that particular output signal would be active. Then, based on the input signal and the output signal, we form a truth table which consists of true or false, that is 0 and A and B. The minterms of the 2 input signal would be A bar, B bar. So, as we observe this truth table, Q0 represent A bar, B bar, Q1 represent A bar, B, Q2 represent A, B bar, Q3 represent AB, Q0, Q1, Q2, Q3 are the minterms of A and B. When we have to get the output of Q0, Q1, Q3 by passing AB as the input signal. When A equal to 0 and B equal to 0, A bar, B bar output would be 1 and Q1 would be 0 because A bar would be 1, B bar would be 1. 1 into 1 is 0. In the second input signal combination 0 and 1, A bar would be 1, B would be 0, 1 into 0 would be 0 for Q0, and 1 into 0 would be again 1, Q2 would be 0, Q3 would be 0. When we take 1 and 0 as the input signal, AB bar, for Q0, the output would be 1 into 1 would be 0, then 0, again 1 and 0. Then for AB, it would be 0 for Q0, Q1 it would be 0, Q2 would be 0, Q3 would be 1. Here is the representation of 2:4 decoder. Now let's discuss about 2:4 decoder implementation. 2:4 decoder implementation means that we are passing two input signal and there are four output signal generated by the decoder. Here A and B are the two input signal. A bar, B bar are the not of A and B respectively. A bar, B bar, A bar, B, A, B bar, and A, B are the representation of Q0, Q1, Q2, Q3 respectively. These are the minterms. We have connected input signal in a unique combination within the decoder. When we are passing A0 and B0, Q0 would be 1 and Q1 would be 0, Q2 would be 0, here it would be again a 0. When we pass 0 and 1 has the input signal, for Q0, 1 into 0 would be 0, 1 into 1 would be 1, and 1 into 0 into 1 would be again a 0, 0 into 1 would be 0. Third input signal would be 1 and 0. So when we pass for this AND gate, 1 bar would be 0 into 1 would be 0 for Q0, and for Q1 it would be 0 into 1 would be 0 again, and here 0 into 1 would be 1, and 0 into 1 would be again a 0. Here for fourth input signal, 1 into 1, 0 into 0 would be 0, 0 into 1 would be 0, and then 1 into 0 would be 0, then 1 into 1 would be 1. As we observe this truth table, output signal is active only at one state, that is in for the first row. When we pass the 0 and 0 has the input signal, then Q0 is the only one minterm which has one, which is active uh, at that input, for that input signal. At 0 and 1, Q1 is active. For 1 and 0, Q2 would be active. For 1 and 1 input signal, Q3 would be active. So only one output signal is active at a for a one input signal. Here is the explanation of 2:4 uh, decoder implementation, where the 2 to 4 line binary decoder consists of an array of 4 AND gates. The two binary input label A and B are decoded into one of four output, hence description of 2 to 4 binary decoder. Each output represents one of the minterms of the two input variable. Q0, Q1, Q2, Q3 are the minterms of the input signal A and B, where high represent 1 and low represent 0. Therefore, high is active whenever the enable input matches the combination of logic circuit in the decoder. The extra input allows the output of the decoder to be turned on or off as required. The output is only generated when the enable input has value 1. Otherwise, all outputs are 0. Only a small change in the implementation is required. The enable input is fed into the AND gate, which produces the outputs. Now let's discuss about 3:8 decoder implementation. Here we pass 3 input signal and it generates 8 output signal. Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7 are the minterms of the A0, A1, A2 input signal. In off state, everything, even the enable input is zero and all minterms would be zero. Where for the first input signal, when all three input signal are zero, y naught is at a one state. When for the second input signal, 0 and 0, 1, the y1 would be at a one state. For third output signal, Y2 would be in the active state. For fourth input signal, Y4 would be in the active state. So on, at the last input signal, the Y7 would be active. Even now, if we observe this truth table, in the output section, only one output signal is active for each input signal passed to the decoder. The 3 to 8 decoder is also known as binary to octal decoder. It is used to convert the binary number into octal number. Here is the representation of minterms y0, y1, y2, y3, y5 to y6 are the minterms and corresponding minterms are represented. Here is the logic circuit for the 3 is to 8 decoder. We use 8 AND gates and 3 inverter to form 3 is to 8 decoder. 3 is to 8 decoder can also be implemented with the help of 2 is to 4 decoder. To form 3 is to 8 decoder with the help of 2 is to 4 decoder, we require 2 is to 4 decoder. Let's consider this to be the first 2 is to 4 decoder and this is the second 2 is to 4 decoder. The output of 2 to 4 decoder would be Y0, Y1, Y2, Y3. The output for second 2 is to 4 decoder would be Y4, Y5, Y6, Y7. This is the enable input of second 2 is to 4 decoder, and when we connect this enable input with the help of inverter, this is the enable input for the first 2 to 4 decoder. These are the steps required for the conversion of 3 is to 8 to 3 is to 8 implementation of decoder with the help of 2 is to 4. Here, first we need to divide three input signals, say A, B, C, into two groups. In group 1, we are passing AB as the input signal for the first 2 is to 4 decoder. And for the second 2 is to 4 decoder, we are passing BC as the input signal. Here A0 is A, A1 is B, A2 is C input signal. Then creating 2 to 4 decoder. Use the first group of input signal to create the first 2 to 4 decoder as I shown here. Use the second group of input lines to create the second 2 to 4 decoder as shown here. Assigning output lines for A0 and A1, Y0 to Y3 are the output signal. For A0, for B and C, Y4, Y5, Y6, Y7 are the output signal. So when we discuss about how it works, now when in this, when we pass 0, 0, 0 to the decoder, here when it is 0 and 0, Y0 would be at active state, Y1, Y2, Y3 would be in 0 state because only one output signal can be in active state for the decoder. To make this Y4 to Y7 also in a 0 state, we connect an inverter to this enable input so that we get a 0 over here because when When we pass 0 and 0, this would be 1, 0, 0, 0. So then enable input for this decoder would be 1 for 0 and 0 input signal. When we complement this, the enable input over here would be 1, so 0. So y4 to y7 would be 0. For the second input signal 001, 001, y1 would be at an active state. So y2, y3, y0 would be in a low state. When we complement the enable input, which is at a 1 state, the enable input in the second decoder would be 0. Hence y4, y6, y7 would be 0. When we pass fourth input signal, then Y4 would be in an active state, then Y5, Y6, Y7 would be in a low state, because only one output signal can be active at for a one input signal. So over here it would be in one state. When we complement this, the enable input over here would be 0. So all this output signal would become 0, and we achieve to get only one output signal for one output signal to be active among all 8 output signals. This is the way how 3 is to 8 decoder can be implemented with the help of 2 is to 4 decoders. Now let's learn about 4 to 16 decoder implementation. In 4 to 16 line decoder, there is total of 16 outputs, because when we pass 4 input signal, it would produce 4 16 output signal, because has according to the formula, when we pass n input signal, there would be 2 to the power of n output signals. So 2 to the power of 4 would be 16. So we 4 is to 16 decoder would produce 16 output signal. Y0, Y1, Y2 till Y16 are the output for 4 input states A0 to A3, where Y0 to Y16 are the midterms for this 4 input signal. Here A0, A1, A2 are A3 are the input signal, where we have passed it to the 2 3 to 8 decoders. 4 is to 16 decoder can be implemented with the help of 2 3 to 8 decoder, where we connect 3 input signal uh, for each 3 is to 8 decoder. So here I have written required number of 3 to 8 decoder equals 2, because M1 is equal to 8, M2 equals to 16. When we divide M2 divided by M1, we get 2. So we require 3 is to 8 decoder. Here is the representation of the minterms from Y0 to Y15. This is the truth table for 4 is to 16. As we observe this truth table also, in this truth table, every output signal, in each output signal, combination of output signal, only at one state it is active for each input signal. Let's discuss about decoder problems. Now let's discuss about the implementation of half subtractor using 2 is to 4 decoder. Normally in half subtractor, we require 2 input signal, and it must generate 4 input output signal. Hence 2 is to 4 decoder is suitable for this half subtractor. When we connect A and B to the 2 is to 4 line decoder, it generates D0, D1, D3 has the output signal, which is similar to Y0, Y1, Y2, Y3 output signal. Here Y0 is A bar, B bar, Y1 is A bar, B, Y2 is A, B bar, Y3 is A, B, sum equal to A bar, B bar, plus A, B bar, which is very similar to XOR gate. Carry is equal to AB. Y0, Y1, Y3 are the midterms. To get the truth table of half adder, let's compare 2 is to 4 decoded truth table. To get sum has the output signal from the 2:4 decoder. When we connect Q1, Q2 with an OR gate, we get sum has the output. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. So we connect Q1 and Q2 to the OR gate. Here D2 is connected to the OR gate. We get a sum. When we compare Q3 and carry output signal of 2:4 and half-added truth table respectively, we observe that Q3 is equal to carry. So D3 is nothing but carry. This is how half adder can be implemented with the help of 2:4 decoder. Next, let's learn about full adder using 3:8 decoder. Normally in full adder, we require 8 output signal by 3 input signal, which is passed to the circuit. So we pass the input signal to 3:8 decoder and it generates 8 output signal. Here we connect Y1, Y2, Y4, Y7 to an OR gate. We get this sum of the half adder. We connect Y3, Y5, Y6, Y7 to an OR gate to get carry as the output. Y1 to Y7, these are the minterms represented in the form of ABC input signal. When we compare the decode 3:8 decoder, truth table, and full adder, we can say that when we connect Y1, when we connect Y1, Y2, Y4, Y7 to an OR gate, we get sum as the value. When we connect Y3, Y5, Y6, Y7, we get carry as the output. This is the way how full adder can be implemented with the help of 3:8 decoder. In the same way, we can implement half subtractor using 2:4 decoder. Here, AB is the input signal which is passed to 2:4 decoder. Y0 to Y3 are the output signal, where Y1 and Y2 are the Y1 and Y2. When we connect to the OR gate, we get a difference, and Y1 is nothing but the borrow. When we compare the truth table of 2:4 and truth table of half subtractor, we can say that Q1 plus Q2 gives difference, and Q1 gives the borrow. So 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is 1, and 0 is 0. In the same way, we can implement full subtractor using 3:8 decoder. Here we are passing 3 input signal, we get 8 output signal. When we connect Y1, Y2, Y4, Y7 to the OR gate, we get difference as the output. When we connect Y1, Y2, Y7 and Y3 to the OR gate, we get borrow as the output. So Y0 to Y7 minterms are represented with the help of input signal ABC. Let's discuss about the problems of decoder, fan out limitation, propagation delays, power consumption, area utilization, complexity, and design effects. These are the problems faced by using decoder. Addressing these decoder problems often involves careful design considerations, optimization techniques, and trade-off between factors such as speed, power consumption, area utilization, and design complexity. Application of decoders are address decoding in memory system, display system, control signal generation, data multiplexing and demultiplexing, priority encoding, digital logic circuit, addressing devices, error detection and correction. Decoders find application in various fields where digital signals need to be interpreted, processed, or routed based on the specific condition. Importance of decoder such as data interpretation, control signal, data routing, address devising, addressing devices, error detection and connection flexibility, versatility, building block for digital systems. These are the importance of decoder, and I end this session here. Thank you.